Date is a new topic. Let's put my heading down before I forget. Math 146, and we're going to be looking at chapter 7. And chapter 7 deals with probability. So I'm going to be going over essentially the introduction to probability today. And there's a lot of numbers in that, a lot of fractions, a lot of percentages. So let's start off with definition. So here we go. The probability of an event A happening is given by this formula. Probability of A is equal to a fraction. On the top are the number of ways event A could happen. So it's very cryptic. Divided by the total number of ways anything could happen. So let's give an example. Suppose I had a dice, and on this dice, right, as you know, dice, you get the numbers 1 to 6. And I wanted to know what's the probability that I roll a dice and I get the number 3. So I'll get a dice and I roll it. And the probability of getting a dice, getting a 3 from a dice, is that there are 6 numbers on the dice and only one of them is a 3. So we would say that the probability of getting a number 3 is 1/6. And you can think of that in lots of ways. Can you think of it like 1/6 of the time, right? If I did it lots and lots of time, wouldn't 1/6 of the time probably be a 3, right? That's one. Now we have 3 different ways to express 1/6. That's a fraction. This here is obviously a decimal. And the third way is as a percentage. And they all have their own strengths and weaknesses. Fractions are very common, and decimals as well as percentages are very common. One of the advantages of decimals and percentages over fractions is that if you want to compare 2 probabilities and you want to know which one is more likely than the other, right? Which one has a bigger probability? When they are fractions.
So I have no head.
When they are fractions, it's hard to tell whether or not those guys, talk a little bit louder or someone, there we go, whether or not they are, which one's bigger than the other. So here's an example. Probability of something happening is 17/13. Probability of something else happening is now 9/15. Now, unless you're really comfortable with fractions, would you agree it's quite hard to tell which one of them is the biggest? Right. So if you convert them into decimals, let's say rounding off as well. So this one is about 0.74, 74%. And the other one is definitely smaller. So one of the advantages of doing a decimal or a percentage is that it's easy to compare 2 together. Another advantage is that if you want to add 2 or 3 different probabilities together, if the fractions end up being different fractions, like you wanted to add a third plus a quarter plus a sixth, isn't adding fractions a little bit more awkward than adding decimals or adding percentages? So that's the plus of why some probabilities are written in this form. There are pluses to fractions. For starters, aren't fractions easy to get because the top number's a number and the bottom number's a number and you're done. The only time you would worry about a fraction is if it was that guy, you would always simplify it, right? So fractions are very convenient. And as long as the bottom number is the same, right, as long as the denominator is the same, it is quite easy to tell which is big, right? And as long as the bottom numbers are the same, isn't it easy to add and subtract? So a probability then is a number that measures how likely something is to happen. When you look at all the probabilities that could happen and you imagine them on a number line, let's say from 0 to 1, or if you convert it to percentages, from 0% to 100%, every probability in the universe is going to be between 0 and 1, or 0 and 100%. Right? I mean, isn't the most you can ever do is everything over the same everything, right? That's guaranteed to be 1. So let's look at the extremes. If the probability of an event is 0, that essentially means this will never happen. So events that have a probability of 0 can't happen, right? So I'm trying to think of some stupid that would never happen. The probability that every politician in America tells the truth is 0, right? That's never going to happen. The probability that I win the lottery tomorrow is 0. How can I say that for certain, that the probability that I win the lottery tomorrow is 0?
Only if you didn't participate or get a ticket.
That's right. I have bought no tickets, so I ain't winning. Right. Now, at the other extreme, you have probabilities that could equal 1. These events are going to happen. So anything that has 100% probability is going to happen. The probability that I throw a coin in the air and it ends up being a head or a tail is 100%, right? It's going to end up one or the other. It's not going to miraculously turn into something else before it hits the ground. That would be 100. Now, right in the middle, we have a probability of a half, or 0.5, I guess, which is 50%. In the English language, we actually use the language of probability in conversations. Have you ever heard people say, oh, it's just as likely to happen as not? You know, a phrase like that. So it's just as likely to happen or not that it rains tomorrow. Doesn't that make, you know, a 50% chance it rains, a 50% chance it doesn't, right? You might even use those words. Oh, the chance that that marriage ever makes it is 50-50. You ever heard a phrase like that? That's just another way of saying, you know, 50% yes, 50% no, right? 50% it lasts, 50% it knows. Right? If someone says that will never happen, aren't they just saying the probability of it is 0? And if they say, yep, that's guaranteed to happen, aren't they saying a probability of 1? So this is a sliding scale, right? From ain't happening to it is. And right in the middle, that's a kind of borderline, isn't it? Half is, you know, chance of happening, half the chance of not. So if you have events very close to 0, then they have small probabilities. And if you have events over in this side, they have large probabilities. So any number that is close to 1, isn't that very close to happening a lot of the time? So if I say the probability it rains tomorrow is 90%, wouldn't you get a good feeling that it's probably more likely than not, right? It's going to rain tomorrow. If I say that the chances that Oh God. The chances that the Democrats gain seats in the midterms is 10%. And that's because what I'm saying there is that that's very unlikely event. Now, casinos know all about probabilities. In fact, the reason casinos exist is that they know the chances of you winning at any game that you play. Right, so when you play the one-armed bandits, those machines are programmed to pay, I think it's 80%. In other words, if you put in $1, lots and lots of dollars, you get about 80 cents back, right? See that 20 cents different, that's profit. So casinos love one-armed bandits. But even if you play blackjack or roulette, all of those, they know the probability that you're going to win, and they always have the edge. They always win more money off you than you're ever going to win off them. Now, that isn't a one-to-one thing. That's like 1 million people gamble. Okay, 10,000 win a lot of money, but don't all the others lose more? And that's how they win. So probability is used in gambling. It's used in business. If you're going to do something, chances are you can't guarantee that this new advertising campaign is going to be effective. Or if we change the coloring, it's going to make people like it more and buy it more. Right? There's probabilities involved in that. There's risk. A simple thing like car insurance. Why is my car insurance less than yours, River? Even although we have identical cars, let's pretend we did.
I'm younger.
Yeah. Why are younger people charged more for the same car insurance than older people? I mean, why do you think they choose it? Say again?
Higher risk.
Higher risk. Do you know that risk is expressed as a probability? So the chances that someone of River's age, I'm not saying you, River, you're very safe, but someone of River's age getting into an accident is 4 times higher than me getting into an accident. So you can see from the insurance company's perspective, shouldn't you pay a lot more insurance than I should? Because they're more likely to pay out on people of your age and less likely to pay out on mine. So this probability is all pervasive. It's everywhere. It's maybe not upfront, but it's going on in the background, like insurance and anything connected to that. So let's look at some probability calculations now. And the ones I'm going to look at are dice, because they're easy. And then we're going to move on to cards, which are much more problematic. And then we're going to move on to, we have time, probabilities with 2 dice. And then we're going to look at picking things from bags. That heading will make more sense if we get to it. We'll definitely get to it next week if we don't get it today. Right, so the dice probabilities we're going to start off with are simply things like this. What's the probability that you roll 1 dice and you get an even number? Well, there are 6 numbers on a dice. And how many of the numbers on a dice are even?
3.
3. There's a 2, a 4, and a 6. So the answer is a half. And I'm just going to leave my answers today as fractions, right? Maybe next time I'll turn them into decimals. Watch when you do the homework next week. If they ask for 2 decimal places, or if they don't ask at all, assume that it's a fraction. What's the probability that I roll a dice and I get a number that's less than a 5? Bottom is 6, that's guaranteed, but less than a 5.
The 2/3.
Yeah, How many things are less than a 5 on a dice? There's a 1, there's a 2, there's a 3, there's a 4. And 4 out of 6 gets you 2/3. There's not an awful lot of questions you can ask with one dice. Agreed, I've pretty much done all of them. So let's look at cards. Now, there's quite a few questions involving probabilities with cards, but not everybody is familiar with cards. So if you are, this bit's a bit boring, but stay with me. We are talking about a standard pack of cards here. So there are going to be 52 cards. So there's no jokers or weird ones, right? Cards are split into 4 suits. In no particular order: hearts, diamonds, clubs, spades. And cards have colours. Diamonds are red in colour. So are hearts. And I know this isn't black, but clubs are black in colour, and so are spades. Which again, you say, yeah, I know a deck of cards. But for the benefit of those who are not familiar with cards, I think it's worth it going over these. Now, each one of these is called a suit. So there are 4 suits: hearts, clubs, diamonds, spades. Now, each suit is essentially identical. And by that I mean they contain the same number of cards and the same kind of cards. And the cards are called ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then you finish with jack, queen, and king, right? So in a normal deck of cards, the ones we're talking about in this question here, the 13 cards in each suit are an ace to a king. And diamonds and clubs and spades have the exact same cards. So you could have an ace of spades, an ace of diamonds. You could have a 4 of clubs and a 4 of hearts, right? They all share the same thing. Are we comfortable with decks of cards now?
Are you teaching us how to count cards for blackjack right now?
No, that is not my job.
I'm just kidding.
You can watch videos and doing that in your own time. So let's do some probabilities. What's the probability that I have a red card? Well, there are 52 cards in a deck, so they're just going to be 52 on the bottom. And if I say red cards, how many of those 52 are red in color?
26.
Right? So there are 13 hearts, 13 diamonds, so that's 26. And do you notice that that fraction can simplify? And if it can be, you should. What does 26 out of 52 get you?
1/2.
Right. Does that make sense? If you randomly pick one card from a deck, isn't there a 50% chance that it's a red card? Doesn't that seem reasonable? If I went and found the probability that it's a black card, you shouldn't be surprised that it's also a half, right? What about the probability that I take one card from a deck and it's a club?
13.
And what does that simplify down to?
Quarter.
Now that you see that, does that make sense that there's a 1 in 4 chance that you get a card and it's a club? Isn't there a 1 in 4 chance it's a heart, a 1 in 4 chance it's a diamond, and so on and so forth? Then you can make them a little bit more interesting. What's the probability that I take a card from a deck of cards and it's a red king? I think I heard 2. Agree? And the 2 red kings, won't they be the king of hearts and the king of diamonds? And that does simplify, not by much, but it does simplify. Does anybody here know which cards are called face cards? Because that's what my next question is going to involve.
The kings, queens, and jacks.
Okay, agreed. Do you know why they're called face cards? It's a very simple reason. If you have a packet of cards, they have faces on, right? The jack's got a little jack, queen's got a queen, and king's got a king, right? So, what's the probability then that I pick one card and it's a face card?
$12.
Correct. You want to tell us where you get it from?
3 face cards per suit, so it's 3 times 4 would make 12.
Makes sense to me. That simplifies, doesn't it? Why don't you tell me what it simplifies to?
1/13.
3/13.
I like the 13ths. Bit 4. Right. If you come across a fraction that's just weird or ugly or just you're not sure if it simplifies, here's the shortcut. Type in the original, 12 divided by 52. Hit enter. Then do math button, choice 1, and it'll turn the answer into a fraction. What's that? 330. There, I'm glad I checked. It's 3/13, isn't it? Eh? Calculator's your friend. Right. Well, let's make it messier. What's the probability that it's a red face card?
Six.
And I'm assuming that it's 3 face cards, but only 2 red suits. And 6 out of 52. I'm getting really worried about this. 6 out of 52. Not trusting my brain this time. $3.26. Yeah. Oh, I just thought of one, not to do with face cards. What's the
40?
probability?
Oh, got a little ahead of myself there. Sorry.
Yeah, you could be. How many cards in a deck are not a king?
48.
Okay. Now, you could add up all the ones that are not a king, but couldn't you kind of make your life easy? Couldn't you say, oh, I know there's 4 kings because they're easy to count. So if I'm not a king, then I'm not those 4, which means I'm the other 48. Do you see my logic there? Take it away and what's left. So you get 48. And I believe if you do that one, oh, I believe you get 12 13s. Please tell me I've done that one in my head, right?
Yeah.
Right. So you could get all sorts of, I'm not doing that. You can imagine, I could have said, what's the chance that you've got a 10 or a jack? Right, when you just count 10s and jacks and do it, right? What's the chance that it was bigger than 5 but less than 9, right? You basically, you count, don't you? You imagine you've got an entire deck of 52 cards. I've even seen students who've told me in the past that they actually got a deck of cards, especially for the complicated ones, and then just went through the deck and took the cards that the description was describing, and then say, oh, there's 8 of them, 8 out of 52, right? I mean, you could do it that way. If it got really messy, like, I don't know, not a king, but it is a face card, something like that, where you have to kind of do more than once. Are we good so far? Right. So here's a side question. Here are 5 events called A, B, C, D, and E. Which one of those are actually possible to get as a probability? So which ones are okay? You could get a probability equal to those values.
Is it A, C, and E?
I'm agreeing with A. What was did you say E?
Yeah.
I'll agree with E. That's all I'm going to agree with. That's the only 2. So let's figure out why the other 3 are bad. Bigger than 1, bad. Can't get a probability bigger than 1. It's like those annoying coaches that say, my men are going to give 120%. If you're really a number person, which I am, can you imagine how that rubs me up the wrong way? You can only give 100%, right? That means you've done it, right? So that's me get mad. What is wrong with that one?
It's a negative.
Right? You cannot get negative probabilities, right? 0 is the lowest you can ever get. 0 means it ain't happening, right? So -2 doesn't mean it ain't happening, right? There isn't another term below it ain't happening. And what's wrong with this one? Which is maybe less obvious, but it is wrong.
Over 1.
Yeah, it's bigger than 1. I didn't put percentages in there, but if I did, 120% couldn't happen, -5% could happen, but 22.1% could happen, right? So, a little side issue, but I know there's a couple of questions at the start of the next section that did that. So let's move on to 2 dice problems. They take, unfortunately, a long time to draw, and I apologize for that. So I'm going to have 1, 2, 3, 4, 5, and 6. And I'm going to go 1, 2, 3, 4, 5, 6. When you roll 2 dice, so you imagine, you play Monopoly, right? Lots of games have 2 dice in them, right? So you have 1 dice that looks like this, right? You have another dice. So you roll 2 dice. I'm making my dice red and green. Then the events, how many things could happen, right? End up being 36. So this event here is a green dice of 1 and a red dice of 1. So I'm going to just set up all these horrible guys. If you have made a nice one of this, you might want to keep it for questions involving 2 dice. Almost done. So these are pairs. They look like coordinates, but what they're representing are pairs of results. One number from the first dice, the first one number from the second. So this would be a 2, a 3, a 4, a 5, and a 6, followed by the second dice was a 1. And this would be the second dice was a 2, but the first dice was a 1, or it was a 2, or the 3, and so on. So now I'm filling in the rest. I'm going to keep this because I do not want to have to do this again. And I should be able to. So that's a 1 and a 3. And a 4.
Starting to
Five.
get linear algebra flashbacks.
Oh, how did they do something similar to this in linear algebra?
Yeah, it's just matrices. and
Oh,
all that.
matrices. I hear you. Yeah, yeah, we don't do that. Thank goodness. Right. This is our dice. This is what the first dice is, and this represents what the second dice is. So, for instance, that one there that I'm pointing at was the first dice. The green one was a 3, and the red one was a 6. Right now, if you look at that, isn't there 6 rows of 6? Can you see 36? So when we do probabilities involving 2 dice being thrown, unless there's some other restriction, we know that the bottom number is going to be 36. Now, when you do a 2 dice story, you can have all sorts of even more complicated probability questions. So I'm going to start off with a very simple one. What's the probability that you get a 1 and a 3? So the green dice was a 1 and the red dice was a 3. And well, if you look at that list, that only happens once. So there's your answer. Now, what's the probability you get a 3 in at least one dice? One of the dice. Takes you longer to write it than it does to do it. There are 36 combinations here. What's the probability that you get a 3 at least once? And I'm now going to do this question wrong. Oh, I know how that works. There's 1, 2, 3, 4, 5, 6 where a 3 happened. And then there is 1, 2, 3, 4, 5, 6 where a 3 happens. So 6 add 6. The answer is 12 out of 36. And that ends up being a third. And I said that is a wrong count. What is wrong with my counting? It's
you
not
counted one extra.
Yeah, didn't I count one twice? I call it double dipping. Didn't that one get counted as one of these 6? And didn't that one get counted as one of these 6? But isn't that just a single thing? You can't count them twice. That's not fair, right? So the correct answer here would be 6 add 5, and that would be 1136. What total? You know, a lot of games you roll the 2 dice and you add them. A lot of gambling games you do that, right? You roll the 2 dice and you add them together. But in Monopoly, don't you roll them together and you get a 3 and a 2, so that's 5 and you move 5, right? So adding is a very common thing. So we're going to look at what's the probability that you get a total of 5. So I look at this guy and I try and find out all the different ways, making sure I don't double dip, that I can get a total of 5. Can anybody count them just by looking at the table and tell me how many?
Is it 4?
Let's check him out. 1, 2, 3, exactly 4. And that simplifies as 1/9. In fact, if you do questions involving totals, do you notice that if you do, I guess I'll call it a diagonal, do you know if you go like this, don't they always add up to the same? For instance, this diagonal here, don't they all add up to 8? So it's not like they're random all over the place. Totals tend to go in little diagonal patterns being added. So here's a question for you. You're gambling with your sister or your brother or your friend who's stupid with lots of money. That would be the best choice. And you're gambling with them and you roll 2 dice and you predict the total. And if you get the total right, you win money, right? And if he gets it right and he or she's not allowed to pick your total, right? So you get to pick first, that's important. And if neither of your totals work, you keep rolling until one of you wins, right? That's the game. I'm going to put you on the spot. So who is you going to be? Sydney, what total would you go for?
6.
Right. So you're going to go for 6. River, you can't pick 6. What total are you picking?
1.
You think you're going to get a total of 1. You are just dumb and too much money. River, if you ever get a chance to gamble with, Sydney, if you ever get a chance to gamble with River, take it. Right? Now, a serious answer, River. What total do you think might be more common than a total of 6?
4, maybe.
Maybe 4. I'm going to pick 7. Right? So we're all in River's mansion because he's got lots of money and he's putting $1,000 down. River has got to get a student loan, so she's put $1,000 down. Right? And I've borrowed it off my wife, so I've got $1,000. And now we're about to gamble and we are going to find out who is likely to win. So let's see what these 3 probabilities end up being. They're all over 36, which is pretty obvious. A total of 6. There's one way of getting a 6, second way, a third way, a fourth way, a fifth way. So won't you succeed 5 out of 36 throws? I could win. 4. One way of getting a 4, right? 2 and a 2 gets you 4. 3 add 1 gets you 4. Looks like you're not going to win very often, are you, River? At least not as often as Sydney is.
I'm a
And
risk
You
then-
put that
taker.
in the wrong spot.
Oh, I did, didn't I? Thank you. And let's do 7. That gets you 7. Second way of getting 7. Third, fourth, fifth, sixth. Does that surprise you that there are more ways to get a total of 7 than there is to get a total of 6? Now, in a lot of situations, that's exactly what people think. You know, if you just said to your friend outside school, you know, if you're playing with, rolling 2 dice, what do you think's the biggest total, the most likely total? Can you imagine why they might say 6? Right, there's, 6 numbers, 1, 2, 3, right? Middle is 3, right? And the other one's middle is 3. Middle and a middle, 3 add 3 get you 6, right? That's the kind of logic that you might have been using. So I think it's very sensible. And yet 7 works. Can you see the advantage a gambler can have if they understand probabilities? Won't I win just a little bit more often than you will? And okay, River, you will win sometimes, you know, the total 4 will happen and you'll think, I'm on it, this is going to work. But it isn't in the long term. Do you see in the long term, won't I win a little bit more than you and twice as often as River? So if you play on a gambling game, it's not on one event. In one event, anything could happen, right? But if you did it lots and lots of times, in the long term, won't I win more often than either of the others? Now, the last thing we're going to talk about here has got a really big fancy name, and it's actually a very simple idea, right? And it's called the empirical phenomena of statistical. No, I did not make this up. Look it up online. It's called the empirical phenomena of statistical regularity. There's a few variations on that sentence, but that is. Now, that sounds very impressive. So if you talk to anybody today, like your husband, Randy, or whatever, your partner, and you say, what did you learn today? You can say, oh, we learned about the empirical phenomena of statistical regularity. Wouldn't that sound impressive? Right? So what on earth is it? Well, what that basically says is, if you take, for instance, this dice game, right? Let's just focus on me, right? It says, if you play this game lots of times, the probability that you win, which is a 6th, doesn't happen every single time, right? You either win or you don't, right? But the chances that you win look like this. Over the long term, doesn't the probability of me winning happens about 1/6 of the time? Right? If you only do it once, couldn't it be 7 doesn't turn up, right? The total is 6, I lose. If I do it 20 times, won't I win about 3 of those times, which is 3/20ths? Then if I do it 3 million times, it comes out as 1/6. So it just means that if you do something often enough, then the number of times that you win, right, the fraction of the times you win will be the same as the probability of it happening. Does that seem reasonable, right? If I throw a coin in the air, isn't the chances I win 50% of the time if I win when it's ahead, right? Now, the first time I throw it, I could win or lose, right? But if I threw it 1 million times, wouldn't I be pretty close to getting 50% of them? Because by that time, the randomness of just a few bad situations will happen. And we have finished for today. So put down your last name for attendance.